Today we will be studying the Pythagorean theorem. We have been using a form of it all year in the distance formula, and you have seen it in previous math classes. The Pythagorean theorem states, in a right triangle, the sum of the squares of the measures of the legs equals the square of the measure of the hypotenuse, or in typical terms, a squared plus b squared equals c squared. In order to do this, you need to remember that the hypotenuse is always the longest side of the right triangle, or opposite the right angle. The other two sides are called legs. Another way to state the Pythagorean theorem is leg squared plus leg squared equals hypotenuse squared. Below you will see one of the demonstrations of the Pythagorean theorem. Here I have a right triangle. It is 6 units on the left side. It is 8 units on the right side. And the question is, how many units is it on the hypotenuse? So if I look at the square that's been built on the left side, square A, it's a square that is 6 units by 6 units, or 6 by 6, which is 36 units squared. If I look at the square that's been built on the second leg, or square B, I can see that it's 8 units by 8 units, and that means its area is 8 times 8, or 64 units squared. According to the Pythagorean theorem, that means that the hypotenuse's square, or that square on the hypotenuse, should be 36 plus 64, or 100. Let's check that out. It's hard to tell because the square on the hypotenuse has been tilted, so I can't just count. So I'm going to break it up into triangles because then I can see what their area is. I know the formula for area of a triangle is 1/2 times the base times the height. On this first triangle, my base is 1, 2, 3, 4, 5, 6. So its area is 1/2 times 6, and my height is 1, 2, 3, 4, 5, 6, 7, 8. And 1/2 times 6 times 8 is half of 48, which is 24 units squared. Now, if I draw another square to the other vertex over here, its sides are 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, 7, 8, or 1/2 times 6 times 8. You'll notice again that that's the exact same triangle. It's just been turned, and its area is 24 units squared. If I come down to the bottom vertex and draw a triangle over, I get a triangle with base of 8 and height of 6, and that area would be 24 units squared. And I can draw one more triangle here, and that also has a base of 6 and a height of 8. So its area is 24 units squared. I found the area of all the parts except this little bitty square in the middle, which I can tell it's 2 by 2, so it's 4 units squared. Now if I add up all of those parts, I have 24 plus 24 plus 24 plus 24 plus 4, which is 100. Exactly what the Pythagorean theorem said I should get for the area on that squared. Well, if the area is 100, I know that each side squared is 100, so my missing hypotenuse had to be 10. Now let's look at a couple of algebraic proofs on the Pythagorean theorem. In this particular proof, we have 4 triangles that are all exactly the same. Each of them has one side equal to A and the other side equal to B. So all the way across, my short side is B and my long side is A, all the way around this figure. I said that backwards. My long side is B and my short side is A. And because of the way these are right triangles, the hypotenuse on each of them is C. So what I have in the middle is a great big huge square which has area of C times C, or C squared. Around the outsides of that square I have 4 triangles. Each of them have a base of A and a height of B, or vice versa. So each of those areas are 1/2 AB. So if I add all my halves together, I have 4 halves, which equals 2 wholes. So the triangles are 2AB. The square in the middle is C squared. Now I also have a great big square around the outside, and that great big square around the outside has a length of A plus B. So the larger square is A plus B squared, or if you FOIL that out, what you get is A squared plus 2AB plus B squared. Well, if I add all of the insides together, it should give me exactly the same area as the outside. So let's see what we have. Inside, I had 2AB plus C squared. Outside, I had A squared plus 2AB plus B squared. Notice what happens if I subtract 2AB on each side. What do I have? C squared equals A squared plus B squared, or using the symmetric property of equality, A squared plus B squared equals C squared. Back to the Pythagorean theorem. Now the other proof just takes the same exact 4 triangles, only it turns them around. So now my outside square is C on each side. So now my large square is, or has an area of C squared. Each of these triangles on the inside had a short side of A and a long side of B, and a short side of A and a long side of B, all the way around. So I had 4 of these triangles, so each of those areas is 1/2 AB. And since I have 4 of them, what I have is 4 times 1/2 AB, or 2AB. So my triangle areas are 2AB. Now notice this time I do have a square in the middle again, but instead of its side having length C, if the whole side here is B and the little piece over here is A, then the missing piece is B minus A. So what I have inside is a little square, and its area is B minus A. So on my small square, what I have is B minus A squared, or B minus A times B minus A. Well, if you use FOIL, multiply that out, what you get is B squared minus 2AB plus A squared. Again, what's inside the square, the large square, should equal the area of the large square. So let's look at that. The large square was C squared. Inside, I had 4 triangles, so that was an area of 2AB, and I had the small square, which had an area of B squared minus 2AB plus A squared. Now notice again what happens. This time it's all on the same side of the equation. 2AB minus 2AB is 0. So I have c squared equals b squared plus a squared, or using that combination of symmetric and commutative properties, a squared plus b squared equals c squared. Now, how do we actually use it? Well, the first most important thing is to figure out which one of those sides is the hypotenuse. You have to do that first. Has to be done first. So if you look at our triangle, our missing side happens to be the hypotenuse, so that's going to be my C. So to find the problem, I just take the other two sides. It doesn't matter which one's A or B, and I have 12 squared plus 5 squared equals C squared. 144 plus 25 equals C squared. 169 equals C squared. Take the positive square root, and C equals 13. Now look at the next example. In our next example, again, I always identify C first, and it was 17. So when I set up my equation this time, it's going to say 8 squared plus, I could call this A or B. I'm just going to call it question mark squared equals 17 squared, or 64 plus question mark squared equals 289. Subtract 64 on both sides. I have question mark squared equals 225, which means that my missing side is the square root of that, which is 15. If all three sides of the triangle are whole numbers, and it does satisfy the Pythagorean theorem, then we call it a Pythagorean triple. Two examples of Pythagorean triples are a 3, 4, 5 triangle, 10, 24, 26 triangle. Those would both be Pythagorean triples. You should be able to easily see what's wrong with these three numbers, and that is there's no way they can be a Pythagorean triple because they are fractions. They are not whole numbers, fractions slash decimals. Okay, the next thing we're going to look at is what we call the converse of the Pythagorean theorem, and it just works it backwards. In other words, we know all three sides, we substitute in and see if it works for a right triangle. So here we go. I have three sides, 8, 10, and 6. So first, which is my hypotenuse? It's got to be the longest side. Largest number here was 10. So I'm going to check, does 8 squared plus 6 squared equal 10 squared? I do some arithmetic. I get 64 plus 36 equals 100. That checks, so it's a right triangle. Try the other two problems, pause the podcast, then check and see how you did. Hopefully you got the two problems right. On number 2, 11 was the hypotenuse. On number 3, 26 was the hypotenuse. Number 2 was not a right triangle. Number 3 was. Now, this is just some extra info. It's not in your book, but you can actually tell based on the Pythagorean theorem if you have an acute triangle, a right triangle, or an obtuse triangle. If the triangle is acute, then when you do a squared plus b squared together, it'll end up being greater than c squared. Now, I have a little bit of a demonstration for that. If the problem is exactly right, then a squared plus b squared would equal c squared, and you would end up with a right angle in this corner. However, if you take c and you make it a little bit shorter, that means c squared is not going to work. The only way that's going to work then is going to be if a and c go in a little bit, or b go in a little bit, so that c can be shorter. That means it's going to turn into an acute triangle. Of course, a squared plus b squared equaled c squared was right. Similarly, if you have a squared plus b squared is less than c squared, it's going to be obtuse because the side will be longer. It's going to spread out the a and the b sides. This concludes our podcast.